All right. Good morning, everybody. And we're almost at the end, second last day of fuel combustion chemistry. So I think there's a dinner tonight. It should be fun. I'm looking forward to that. And I forgot my jacket, and it's already freezing in here. So I'll try to keep moving to keep warm. So, okay, today we're going to discuss more about, again, how we can apply kinetic rate rules to build a kinetic model. And that'll take maybe the first hour and a bit. And then after the rest of the class, we'll start talking about experiments, different types of experiments that combustion community actually utilizes to understand more about kinetic processes that are of relevance to like gas turbines and engines and boilers and other types of combustion systems. So yesterday we were talking about the different types of reactions one would want to include in a kinetic model if they want to predict high temperature combustion. This is anything you would need to predict combustion phenomena. Just again, as a rule of thumb, anywhere above 900 degrees Kelvin. So if this is a ignition delay curve, and this is, say, 1,000 over T, so this is high T, right, on this direction. This is low temperature. So if we say 1,000 over T of 1 is about 1,000 Kelvin. So typically you'll see if you do experiments or modeling, do you have an ignition delay time curve at high temperatures? That's pretty much a straight line. Arrhenius. This is actually Arrhenius law, right? So tau versus 1 over T, it follows an Arrhenius type kinetics. Or this could be the log. This could actually, typically we plot this as the log of ignition delay time because it is spanning multiple orders of magnitude. This typically around 1,000 Kelvin, or ballpark you're around 1 millisecond for any real type of fuel, gasoline, diesel, jet fuel. And that'll vary with pressure, right? If you increase, this might be around P of 20 bar. And depending on the fuel, depending on the pressure, you'll have some changes in the variation depending on the equivalence ratio and so on, yeah? So at high temperature, if you want to predict this curve at high temperatures, say ballpark above 900 Kelvin, these are the types of reactions you would need to have in your model, yeah? But of course, diesel engine combustion, knock in the N gas of a spark ignition engine doesn't happen at 950 Kelvin and above. It starts happening at lower temperatures. It starts happening as soon as the fuel is introduced to the air and the temperature reaches anywhere above 550, 600 degrees Kelvin. The units here are 1 over K. Okay. So typically your curves might look like this, coming down to lower temperatures. So you see here in intermediate temperatures, let's say this is around 750 Kelvin, and below this is below 750 Kelvin. You start to see some change in the kinetics. Yeah, and so what happens here, very different phenomena. You will not be able to predict any of that with just these 9 reaction classes. You'll need to include more reactions. These are things related to intermediate temperature chemistry and low temperature chemistry. I will maybe just present those briefly, but I'm not going to talk in detail how we assign kinetic parameters because that'll take another 5 days on its own because there's so many different reactions that are contributing to the phenomena in this region. We need about 12 to 13 additional reaction classes, and the rates of those are much less well known than what we have for high temperature combustion. But we'll try to just present those briefly so you understand what the complexities are. So yeah, and this high temperature ignition, this region here, this is what we're looking at. This is also the same phenomena that governs the speed of a flame propagation rate or flame speed. It will govern the high temperature ignition of a flame. So diffusion, flame ignition, extinction, and so on. Also species formation. If you want to predict soot formation, well, soot always formed in the high temperature combustion region in a flame. So typically you need to get the base flame structure correct in terms of its types of species that are being formed, and then you can start predicting the soot process. So this would again form the basis for your initial model to predict soot formation. Then you'll add other reactions for the growth of your PAHs and soot. And in this scheme of 9 reaction classes, the most important ones are going to be the first 4 or 5, yeah? And it's going to depend, of course, on the equivalence ratio and the environmental conditions. So if you're running at very rich conditions, meaning fuel oxidizer lean condition, you're almost at pyrolysis. So let's say phi above 2, yeah, 2 or more, yeah. You're really going to start looking at the first reaction class a lot, unimolecular fuel decomposition. There's not much oxygen around, so the initiation mainly happens from scissions of the fuel molecule. We talked about that yesterday. Once you're coming below phi of 2, phi of 1.5, 1, and then very lean conditions, it's hydrogen abstraction. And most of the time in combustion, we're burning near stoichiometric or lean because we want to, of course, mitigate. In an SI engine, you're burning near stoichiometric. For what reason? Anyone can say why in an SI engine we're always near stoichiometric? Yeah, so your catalyst cannot operate if you have excess oxidizer in the exhaust stream. Of course, we would prefer modern engines. We want to go leaner. Yeah, lean SI engines are of interest, but then your 3-way catalyst doesn't work. So they're trying to figure out ways, other types of catalysts you can have for after treatment. Your diesel engine is globally very lean, yeah. So maybe phi of 0.2 to 0.3 global, but of course it's rich in the regions because it's a non-premixed combustion. So the region when the fuel is first injected, they typically say in a diesel engine, so in an SI engine, okay, N-gas, ignition, or knock, it happens near 0.1, okay? Ignition is near 1, okay? Near, say, phi of 1. Sometimes it's a bit leaner, 0.95 or 1.05 in that region. But in a diesel engine, in a compression ignition engine, this whole phenomena happens at phi of around 2 to 3, okay? And that depends on the load. And this is, who discovered this? Was a scientist in Sandia National Labs, Combustion Research Facility, John Deck. I don't know if anybody study engines, heard his name. Okay, John Deck. I think he's retired now just in the last 6 or 7 years. Probably the best engine experimentalist I've ever seen, yeah? This guy can take an engine and he can investigate everything inside of it with laser diagnostics, imaging, different types of sampling techniques, and understand exactly how the combustion process happens in an engine. And he built something called a phenomenological model of a diesel engine. And he says you spray, this is the injector, and the fuel's coming out as droplets, okay, into a plume, into the cylinder, and this is all air, hot air, yeah? You're injecting your fuel into a very hot environment, and this kind of forms out. First, it starts vaporizing, okay, into some kind of a gas because it's entering hot air. And then eventually, you have these first ignition points, okay? And he was able to see this with optical diagnostics, and then using things like chemiluminescence, he can determine the air-fuel ratio in the region where ignition happens. And then depending on the load of the engine, depending on how much fuel is used, he said this happens, again, around phi of 2 to 3. Yeah. And actually, I think the paper came out like 2005, John Deck's seminal paper. And actually, these guys don't publish in Combustion and Flame and Fuel. They publish everything in SAE. So actually, some of the nicest papers you see about understanding kinetics in engines is not even in our combustion journals. They're all in the SAE journals, and typically the World Congress. So, and they tell you a lot about, okay, if I really want to understand combustion phenomena relevant of diesel engines, I shouldn't be studying ignition and doing experiments near stoichiometric equivalence ratio or even lean. Because we conventionally think diesel engine is globally lean. Yes, that's after ignition. But at the point of ignition, it's very rich. And you need to understand the chemistry under those rich conditions. And that's why, you need to, I encourage you, when you try to understand kinetics, don't just think about the fundamentals. It really has to be relevant to the real systems and understand what the industry guys are doing, how they're looking at the process, and what are the real conditions there. And then he also said he also found the temperature, because he had a laser-based temperature technique. And he says ignition happens phi of 2 to 3 and around 750 to 900 Kelvin. Again, depend. And that's also the first time people started to get more interest in the low temperature chemistry, and low and intermediate temperature chemistry. So it's sad these days. I think Sandia Research Lab lost a lot of its funding, for combustion research. They had a lot of really good engines people. They had to let them go. A lot of good laser diagnostics were developed there. Because of funding reasons, they had to scrap some of those programs. But if you read back, 10, 15 years, the best papers, applied combustion kinetics and in real systems you can find from Sandia. All right, so that goes to say that, okay, at rich conditions, different fuels are there. Depending on the temperature, different reactions will be important. But typically, in most conditions, we care about hydrogen abstraction because that's what's initiating and propagating the overall combustion process. So we talked about this already yesterday a bit. Remember, these abstractors that are important are hydrogen radical, H radical, OH radical, HO2, hydrogen, which is hydroperoxy radical, and methyl radical. Methyl comes from the fuel. All the other ones are coming from the hydrogen that's removed from the fuel and oxygen, reactions with oxygen. And we said in this molecule, 4-methylheptane, you could have, I think we said 1, 2, 3, 4, 5 different abstractions that are possible. And we could start at a simple case, just developing rate rules for abstractions from these different sites for different types of abstractor molecules. So H radical, OH, methyl, and HO2. And if you plot these, you see on a per carbon site basis, they're all pretty much the same, so you can't neglect anyone in terms of their rate constants. And then I went on to show these nice even more elegant rate rules from groups at KAUST and Argonne National Lab, which were actually measured, right? Measured in shock tubes. And again, how did they do this? Well, they take a molecule, it's called tert-butyl hydroperoxide. Or TBHP, okay? How does it look? Well, it's a tert-butyl, so there's a carbon, a carbon, a carbon, carbon, 4 carbons, a tert-butyl group, and then a hydroperoxide. And there's, of course, hydrogens here. And they introduced this to the shock tube. This is a shock tube. The driver gas is here. We'll look at more detail after. This is the driven section. So they put your TBHP in here, plus some fuel. And then you break the diaphragm, a shock wave propagates, it compresses this mixture, and this molecule is very unstable in the sense that this bond here, this OOH bond, this tert-butyl group is pulling electrons away from the oxygen, this OH group is pulling electrons away from this oxygen, makes it highly delocalized. It allows this bond to break somewhere around 500 degrees Kelvin or so, yeah? And so as soon as this bond breaks, you make a lot of OH radicals. And they have a laser diagnostics. Laser is shining in here, typically through some optical ports. This is a laser for detecting OH. And they don't even care about the concentration. They just care about the signal of the OH because they want to see the decay in OH. And Yeah, that bond breaks, and the OH starts reacting with the fuel and abstracting hydrogens, and they just track the decay of OH radical as a function of time, and they fit a rate constant to that at different temperatures. So depending on the driver gas, the shock speed, they can get different temperatures, compressed gas temperatures, so to speak, and they can start to develop a plot of K versus 1 over T, and they fit the rate constants. Now, similar to group additivity, they don't know exactly which site the OH is taking the hydrogen from. It's taking it from all the sites, right? But they can get they're determining the total rate of OH plus fuel. And then they keep changing the fuel, and so they start very simply with ethane. Yeah, ethane only has 2 carbons, and you get K total OH, yeah, abstraction from all these hydrogens. And then if you go to propane, they do it again. Yeah, they measure the K total, and they do it to butane and heptane. And then they just assign some rules for certain groups. So because propane has 2 methyl groups, this one has 2 methyl groups, that has 2 methyl groups and 1 secondary group. Then they start to apply these rules, and they do this for many different molecules. And they build a table like this. For every type of carbon in many different types of hydrocarbons, you get the rate constant for abstraction. They're not directly measuring, right, the abstraction from this site. They measure it as a whole molecule, and then they back calculate. It's again an approximation, but it seems to work. It works very well, and it agrees fairly well. If you do calculations, they will agree quite well with these experiments. And you can do this for anything. You can take aldehydes, ketones. You can take benzene and put it in there, and that's how they measure abstraction rates. And these experiments, so yeah, Stanford does them, KAUST does them, Argonne does them, and several groups around the world, they have the shock tubes equipped with the laser diagnostics to do these types of measurements. Okay, so if you were to look at different types of rate constants for abstraction, I show you here OH is typically very fast. H is also very fast. Things like methyl and HO2 are slower. Does that mean they're unimportant? No. Okay, because at different points in this temperature, say, regime, different abstractors become important, okay? First of all, at low temperature, it's mainly OH, okay? In this regime here, OH is your most important abstractor, and that's because as the low temperature mechanism proceeds, OH is the one is a radical that's produced the most after many intermediate molecules are decomposed at low temperature. At this region, HO2 is the most important. HO2 and OH, yeah? Both of them are very important in this intermediate regime. And then in the high temperature regime, it's mainly H and OH, okay? And the reason is, if you have a molecule and it eventually breaks down, let's say this molecule breaks down, it forms ethyl radicals and methyl radicals. Eventually you're going to have to make hydrogen. Eventually you're going to start breaking off hydrogen molecules from your carbon chain, and remember the carbon-hydrogen bonds are the most strong, yeah? So they take a high temperature to dissociate. So after 1,000 Kelvin, all these hydrogens, they start leaving, and then at high temperatures, hydrogen is the most important radical. So again, if you're trying to predict something like flame speed, yeah, hydrogen is very important, OH is very important. If you're trying to predict low temperature ignition, actually hydrogen radical doesn't play that important role. It's mainly the OH and the HO2. And remember, kinetics is not only the kinetic rate constants, it's K times the concentration of species. So at different temperature regimes in different combustion environments, you have different concentrations of radicals, and that's what, it's not only the rate constant that matters, it's the concentrations of these species. And again, at lean conditions like HCCI engines, HO2 is very important. because there's a lot of oxygen around, so HO2 radical becomes important. Problem is, we don't have good rates for abstraction by HO2. Nobody can measure this, actually. It's been a problem. People have tried for the last 10 years to do a shock tube experiment to measure abstraction of hydrogen radicals from different fuel molecules using HO2. The problem is we don't have a precursor. Yeah, you cannot, like we have here, TBHP quickly makes OH. Ideally, you would like something that breaks off here at an intermediate temperature to make HO2, but yeah, it doesn't happen like that. And it's not easy to find a precursor that readily makes HO2. People have tried, I think, with methyl peroxide, methyl hydroperoxide, but still it's very difficult. So there's no direct measurement for HO2 abstraction. We rely on calculations. So, I mean, these are just some calculations from different groups like Karlsruhe and Galway. And typically if you go out, the calculations are off. There are differences between like factors of 2 to 4 times. So, 2 to 4 times is the big calculations are complicated because HO2, as it comes in and tries to pull a hydrogen, okay, this oxygen group forms a hydrogen bond, okay? And the transition state for abstraction of a hydrogen using HO2 from a fuel molecule has a hydrogen bonded transition state. And this is very difficult to calculate from quantum chemistry perspective because hydrogen bonds are, they're kind of like van der Waals forces. They're very weak bonds. So when you look at the transition state, it's very difficult to identify, how that bond really happens. And that's why different people will try different methods, theoretical tools, and they come up with different answers. And the range is about, anywhere from 2 to 5 times difference in the rate constant that comes at the end. So that's the situation we're in. Yeah, we don't have good rates. This plot just shows, if you change these rates by a factor of 2, it has a pretty big effect on the ignition time in the region where it matters. In the region that I said here, where HO2 is important, intermediate temperature ignition, that rate of abstraction has quite a big effect, an agreement with data. At low temperatures, it doesn't have an effect. At high temperatures, it doesn't have an effect, but in this intermediate region, around 950 to 1050 Kelvin, it has an effect. And why is that? Well, when HO2 reacts with, say, we had what, C8, H17 was our fuel radical, or sorry, with the fuel, C8H18, it makes H2O2 plus C8H17. And if you remember from our very basic hydrogen-oxygen explosion diagram, one of the key intermediates in that explosive diagram, especially at the high pressures, they said, when we looked at hydrogen explosion explosivity diagram, at high pressures, they get HO2 radical being formed, and then HO2 would react with hydrogen to make H2O2, and then H2O2 dissociates to 2OH, radicals. And of course, OH is then very reactive, so that leads to the ignition. And this dissociation happens at around 950 Kelvin. Anywhere from 950 to 1050, depending on the pressure. Yeah. So again, so everything that happens here is governed by H2O2 decomposition. And in order to make H2O2, you need HO2. And therefore, the rate matters a lot. Yeah. Okay, so we'll skip over that. How can we get these rates? Again, ideally, someone has calculated it. Calculations have errors. Someone has measured it. Measurements are the best, but not many measurements out there. So again, other kineticists have developed what we call Evans-Polanyi correlations. So simple correlations, simple rules of thumb you can use to estimate the rate. So it just says, let's say HO2 is reacting with ethane and with propane. Well, and if you have some estimate for HO2 plus ethane, you can try to take that estimate and move it for HO2 plus propane. And the way they do this is they say that a radical reacts with all molecules. The A factor is always the same. So if you have a A times T to the N. Again, these are simple rules of thumb. They say a radical abstracting a hydrogen from another molecule, the A factors and the N's, the pre-exponentials, should be roughly the same. Because if it's governed by collision theory and so on. Again, it's just an approximation. It's not necessarily true. But this is the assumption they make. And they say the only thing that should change is the activation energy of the reaction. And that's based on the bond dissociation energy. Because different molecules have different bond dissociation energies. So the only thing that changes in your rate equation is the activation energy. And then they provide this equation. So the activation energy for your new reaction is the activation energy for the reference reaction, the one that you know, times F or minus F. F is some factor, fitting factor, multiplied by the difference in heat of formation for the reference reaction and the new reaction. This difference is what we call the differences in the bond dissociation energy. So again, this hydrogen here has a bond dissociation energy of 105 kcal per mole. But this one here has 98 kcal per mole. So if you want to draw some correlations between these two molecules, these two different bonds, you just take the difference in those bond dissociation energies. In this case, it's 7, yeah? And you multiply it by F, and then you take the activation energy for the reference reaction and subtract that from the new reaction to get the new activation energy. And then they give a table like this. The key thing that matters here are the F factors, yeah? So you can see here, it tells you how sensitive a radical is to the bond dissociation energy. So something like H radical, you would take the bond dissociation energy and multiply it by 0.65. And that tells you H radical is more sensitive to the bond dissociation energy. Something like OH is only 0.5 factor. So OH is less selective. It takes molecules, it takes off hydrogen radicals more effectively regardless of the bond dissociation energy. And similarly, NH2, we use this one a lot in ammonia combustion mixed with hydrocarbons because nobody has measured NH2. If you take ammonia, right, the first initiation reaction for ammonia is NH2 plus H. And this is a radical, and NH2 goes, and if you mix ammonia in a turbine with methane or with diesel fuel, which is happening in some parts of the world, they take ammonia and they blend it with methane for power generation in Japan. They're trying to blend ammonia with diesel for marine engines today. So then this NH2 has to go and react with the fuel, like N-heptane or diesel fuel. And people don't know how that abstraction happens. No one has measured it. So you come to these simple tables. These guys came up with a rule of thumb already in the 1990s for NH2. And they said, okay, it's 0.23 times the differences in the bond dissociation energy. It works. It's a rough approximation. And again, you do what you can to build the model at first and until new information comes about. Okay, so that's abstraction. Then after you abstract your hydrogen, you have a radical, right? A fuel radical. We call this an alkyl radical. So for the 4-methyl-heptane, we have radicals that can be made when you pull off a hydrogen. And these radicals undergo a beta scission reaction. Yeah, and we talked about that last time. Once the temperature is high enough, this radical will undergo a beta scission. So this is the alpha bond, this is the beta bond. That bond will break, it'll form an alkene, a double bond between the two carbons, and another radical. And the radical is here. And this radical can undergo beta scission again, and so on. And that's how, at high temperatures here, the fuel radical starts falling apart. The fuel starts breaking down very quickly once the activation energy for these reactions happen. So yeah, beta scission reactions happen in all fuels. And this is how the fuel starts breaking down at high temperatures. So take a minute, talk to your neighbor. How many beta scission reactions are possible for 4-methyl-heptane? So you got to think, how many radicals did we have? And from those radicals, what are all the possible beta scissions? So take a couple of minutes, write them down with your neighbor, and tell me what you think. All right, did anybody come up with an answer yet? You had one? 6, okay. All right. What's the first one you said? How did you get 6? Okay, that's one way to do it. Well, I think it's more than 6. But it's good. Getting closer. It's a good start. Anybody else? 13. You say 13? Okay, and what was your process to figure 13? How did you get to 13? Okay, you did CH and CC. Okay, let's just forget about the CHs, just the CCs, okay? So what did you do? You first you're gonna think about all the radicals, right? How many radicals did we say there are? 5, right? So, okay, here's one of them, right? If the radical's here, you break here, this is 1, yeah? If the radical's here in the middle, second carbon, how many do we have? Also only one possible beta scission, right? So that's 2. If the radical's here, how many do we have? We have 2, right? Because you can break this side, you can break this side, but you can also break this side. There's actually 3, yeah? So now we're at 5, okay? If the radical's here, you can break this side, that's 1. And you break this side, it's the same thing though. It's symmetric, yeah? So that's only 1, 6. And then the last radical is the one here, right? And it can break this side or this side, but it's the same thing. So there's 7. Yeah, so he was close. 6. So there should be 7 carbon-carbon beta scissions. If you have hydrogens, yes, there'll be more. But again, carbon-carbon are the main ones. And so you're going to write these out. And again, what do we have? We have now This was 1. Let's just take a look at the second one. The second one would have made a methyl radical plus a long chain alkene. So remember, if the radical was here, sorry. Okay, this would have been the third one. If the radical is here, one side, you could have made this CH3 plus 2-methylalkene. If the radical was, so this was the third one, let's say. Let's say the second one was here. The second one would have made propene plus an alkyl radical. No, actually, I'm sorry. This is here. One of the possibles is you would break here. So you would actually make pentene plus propyl radical, okay? So like this, you'd have to write them all out. And what's the difference? Well, in all the different products, you're breaking different types of CC bonds, and you're forming a stable species and a stable olefin and a radical. And you got to figure out now rates for all these things, okay? You got to figure out the rates of how these types of decompositions happen. It's hard. It's hard because we don't have many rules for these kinds of things. But typically what we do is we, as I said, for unimolecular decomposition, we put the rates in the reverse direction. So we say a radical adding to some double bond, we can try to prescribe the rate for that. So let's say a methyl radical adding to the double bond of a carbon-carbon at the end of a chain. Or here, a propyl radical adding to a carbon-carbon bond to a tertiary, again at the end of the chain, inside of the chain. Here, a long chain carbon alkyl molecule adding to an ethylene. So like this, we try to do it based on the recombination direction and then calculate the rate of dissociation of the radical from the thermochemistry. So this is for H plus radicals. There's a paper from Curran in 2006 for small molecules trying to document H plus alkenes, the rates. We can use these same rates. And then also for carbon-carbon addition, there's a bunch of rules that have been made for small molecules. Again, this is how we would take these types of rules that were made for small molecules, and again, based on the orientation of the carbon-carbon additions to a radical site, we would prescribe the same rules. They're just rough approximations. They're not exactly correct. I'll show you in a few slides how people actually measure these rates for a long chain molecule. And this is kind of what these are the rules. So Sang has measured some of these things in his single pulse shock tube. And we'll talk about those experiments. And these approximations by Curran, they're within a factor of 2 or 3. So that's kind of, we said high-level theoretical calculations are the factor of 2 to 3. These kind of simple estimation tools are also factor of 2 to 3. So a good chemist, a good engineer with following the rule of thumb should come pretty close. But if you want to get very high accuracy, let's say within a factor of 1.5, you've got to go to a very robust experiment or some type of theoretical chemistry. And I just skip over. So this would be the rules I apply, yeah? This was a paper from, again, from Wing Sang's group in NIST. They did a measurement of all the radical decompositions for 2-methylhexane. Yeah, it looks something like 4-methylheptane, which we are studying for our exercise. So we could use the rules of all the different scission reactions from this molecule and apply the same kinds of things for the 4-methylheptane. One thing to note is these reactions, decomposition reaction is pressure dependent. It's always pressure dependent. And remember we said why that's the case, yeah? So we talked about those reactions which can either fall into a well or chemically. Oh no, sorry. This is your standard Lindemann fall-off type reaction. Any decomposition reaction, we showed in I think the first day or the second day how they have pressure dependence. So this is not a chemically activated reaction. If you have an alkyl radical, and it has to dissociate to form another radical and an olefin. Because it's a unimolecular reaction, it will be a pressure-dependent reaction. So what happens at low pressures, we have a slower rate, and as the pressure increases, the rate increases. And that was your standard, your Lindemann fall-off curve. So we have K naught at low pressure. It looked like this, right? This was K as a function of P. And at low pressure, we had, how did it look? We had a rate that looked like this, and then it went up like that, and asymptoted kind of at high pressure. And then we had to fit this low pressure and this high pressure and some intermediate fitting function to describe this pressure curve. And this was the K infinity. This was the K low pressure or K naught. And we have to put some function for that. So this, it basically says at different pressures, we have different rates. And then again, K is also a function of temperature. So I just plot these as different lines. And this shows you how the fall-off changes as a function of temperature. So actually, fall-off reactions have more dependence at high temperature than at low temperature, because that's also when the activation energy is overcome for the fission reaction. And you see here, so above 1,000 Kelvin, you can have a almost an order of magnitude difference between 1 bar and 1,000 bar. Again, do we do combustion at 1,000 bar? No, we're typically 10 to 100 bar. So we're in this region. But still, there might be a factor of 5 difference. Now the question is, do you need to include now the pressure dependence for all these reactions in your combustion model? Because that's going to be quite hard. Again, depends what you want to predict. So I do a simple test. Usually what I do first is I'll do this test for one molecule and see, is it really important? And you see here, if you calculate ignition delay times, in this case, I built a model for 2-methylheptane because I had all the rules for it. And I see, okay, for this class of reactions, if I include pressure dependence and if I don't, what is the effect? So the lines are without fall off, means no pressure dependence, and then the symbols are with fall off, and different equivalence ratios, different temperatures, and all the curves are pretty much the same. Yeah, there's no effect really of pressure as it manifests itself on the ignition delay time. It doesn't have an effect really. And similarly, this is again more conditions. So this was at 1 atmosphere. This is at 10 atmospheres. Yeah, this is at 20 atmospheres. So even you go to high pressures, it doesn't make much impact. And for something like flame speed at 1 bar, you don't need really to include all this fall off. Now you ask yourself, why is that the case? Now, why is it that the rates are changing by a factor of 5, 10, but still there's no effect as it manifests itself on things like flame speeds and ignition delay times, yeah? Well, the reason is because the fall off is happening for all of these different channels about the same way. Yeah, the rate of all these channels of alkyl radical scissions have a pressure dependence, and the pressure dependence is roughly the same for all different types of channels. So what really matters in a combustion process is not the rate of the actual reactants, it's something we call the branching ratio. So how important is one channel versus another channel? Because that determines what radicals are formed, and that eventually determines the amount of small radicals that are formed. And it's the amount of small radicals, we call that the radical pool, which sets off the ignition event. So, and what happens if you change pressure? Well, from 1 bar to 10 bar to 100 bar to 1,000 bar, the branching fractions to all these different channels doesn't change that much. They're always the same, regardless of the pressure. So basically what's happening, you're canceling out the errors. Even though the pressure is increasing, the rates are changing, they're all increasing or decreasing by the same amount. They're canceling each other out. In the end, you get the same amount of radicals, which leads to the same overall ignition phenomena or overall flame speed phenomena. So again, some ways to simplify the model. Again, I'm not telling you neglect pressure dependence. It's interesting, yeah. Many people study pressure dependence for different reactions just because There's a lot of interesting physical phenomena, chemical phenomena that are there. But in cases when we're trying to build models to predict things like flame speeds, ignition times, sometimes we set aside these, more detailed aspects of the model to simplify just the building of the mechanisms. All right, and then in addition to decision of the alkyl radical, there's one other complication. The alkyl radical can also isomerize. So there's another class of reactions one has to consider, okay? And what happens is, for this radical to break, it typically requires about 1,000 degrees Kelvin for those CC bonds to break. But alkyl radicals can be formed before that. And in this intermediate temperature regime, they can start isomerizing. And isomerizing just means that a hydrogen from one place in the molecule moves to another place. Yeah. So you have these different hydrogens. You pull off a hydrogen here. Well, this molecule doesn't like the hydrogen necessarily to be here. Actually, it's more stable if the radical site is at the tertiary rather than the primary. So actually, it might try to move the radical site here and move the hydrogen over here. And that's called an internal isomerization. And you can think of it like an internal abstraction. So the abstraction doesn't happen from another biomolecular partner. It happens from within the molecule. The molecule bends over itself. It grabs the hydrogen and moves over here. Yeah, and it does that to stabilize itself because it doesn't want the radical on the sites which are the most unstable. So it undergoes an internal H-atom migration or internal abstraction. And we have to consider those reactions. Yeah, those reactions are shown here. This is shown for 1, 2, 3, 4 N-heptane. Yeah. For N-heptane, you form what we call an octyl radical, and this radical can isomerize from 1 octyl. It can go to 2 octyl, so the radical site can move to another side. And like this, the radical site might bounce around different locations at different rates, depending on the temperature. So these isomerizations we need to consider. Yeah. Now, how do these isomerizations happen? Well, how it happens is the molecule is bending over itself, and it's forming a ring. So let's see how this looks. You can say if the radical was here to start off with, in order for it to grab a hydrogen from somewhere else, it has to bend over itself and grab that hydrogen. And in order to do that, the molecule has to change its orientation. So it might come like this, a carbon here, and then this radical starts coming close to this hydrogen, and then it's able to pull it. So you can say the transition state is a ring structure, okay? And this ring has 1, 2, 3, 4 different carbon atoms in the ring. And we call these again. So these are internal isomerizations. The transition state forms a ring structure, and that ring has to be stable, okay? So we go back. The very easy way to look at it is we have different types of ring structures that can be formed based on the distance between the atoms. And what I showed there, we call them 5-membered ring, 6-member ring, and 7-member ring. So if we just count from the carbon site, 1, 2, 3, 4, 5. Okay, this hydrogen to be abstracted is a 5-membered ring transition state. If I count again, 1, 2, 3, 4, 5, 6. This hydrogen would require a 6-membered transition state. So this one is 5, this one is 6. Like this, we have 5, 6, and what did I write there? 7. 5, 6, and 7-membered transition states are possible. And we know this from basic chemistry, right? If you look at cyclic hydrocarbons, yeah, cyclic hydrocarbons like You can have cyclopropane. It's a triangle, right? This is carbon, 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 cyclopropane. Cyclobutane is a square. Yeah? Then what's the next one? Cyclopentane is a pentagon. And then, that's how cyclopentane typically looks, yeah? And then, this is cyclopentane. So this is C5, ring. And then the most stable is cyclohexane, C6, and then cycloheptane. And that's again because here the carbon-carbon bonds are too close together. There's a lot of ring strain. It's unstable. Again, here, 90 degrees, very unstable. Then you start to come to cyclopentane, I think 105, and then 120 degrees between the bonds. It's more stable. So rings of certain bond angles are more stable. It's the same thing we're applying here. So when the transition state has 5 members, 6 members, 7 members, it looks like these very common hydrocarbons, and they're the ones that are more stable. And so we apply the rules based on that. Okay, we're not going to answer this question, because there's a lot of unique isomerizations in this molecule. I think about 11 of them. But again, on your own time, you can draw them all out. You have to consider all the 5, 6, 7-member transition states. And then, again, there's rules for this as well. So Wing-Sang and others, they've developed rules for these different types of transitions states, 5-membered, 6-membered, 7-members, from primary site to secondary site, from secondary site to tertiary site. And we apply those same rules in the development of the new model. Okay, I will skip this one and talk about how we can measure these things. So again, the group from NIST, they've also measured many of these rates. And it's a very elegant experiment, okay? So what they do here is they want to measure the decomposition and isomerization rates. And they have to do these together, right? This molecule wants to, if the radical is here, we said it can undergo beta scission, but at the same time, it can also undergo isomerization. So these are actually not decoupled reactions. This radical can do one or the other. And again, there's many different radicals, and they can both either isomerize or undergo beta scission. So he has to build an experiment which measures all of these rates at the same time and try to find out which channel has which rate constant. And how they do this is, they have a shock tube, okay? A single pulse shock tube, and they fill it up with a mixture of here 5-methyl-hexyliodide and 1,2,3,5-trimethylbenzene, some chlorocyclopentane, and some chlorocyclohexane. What they do is, first of all, what is this hexyliodide? Well, what they do is they start with the parent molecule with no radical, right? And they take one of the hydrogens and they replace it with an iodine molecule. So using synthetic organic chemistry, they make this molecule, okay? And this molecule now has hydrogens everywhere and one iodine replacing one of the hydrogens. Why would you do that? Can anybody think why you would replace one of the hydrogens with iodine? Yeah? Exactly. So this is just like that tert-butyl hydroperoxide had a very weak OH. Now this CI bond is extremely weak. Like iodine is pulling away electrons much more than hydrogen. So the bond dissociation energy here is very weak. As soon as you heat this mixture, the first thing to fall off is, like I said, the iodine, and you'll make the radical here. So you know exactly where the radical is going to be. So now he knows I can do this experiment with iodine here. I can remake the same molecule with iodine here. I could do it with iodine here, but he doesn't bother with that. Because anyways, once you make the radical, it's going to isomerize. So it doesn't matter where he puts the iodine to start with. He just needs to make a radical to start, yeah? And make sure this radical is produced in sufficient quantity. Second thing he puts are two different temperature standards, cyclopropane and cyclohexane. So he knows these molecules, if I heat them up in the shock tube, they will always dissociate to the same products depending on the temperature. So they're like internal standards he uses to determine the temperature after the incident shock. So then he knows the temperature very well in the system. And then finally, he has something called 1,2,3,5 trimethylbenzene, or 1,3,5. So it's benzene with 3 methyl groups, so 1, 3, and 5. Why does he have this? Well, he has this as a radical scavenger. So once the reaction is initiated, this this I falls off, you have a radical, then it's going to start breaking down, like you're going to have alkyl radical scissions, beta scissions, you're going to make things like CH3, you're going to make things like C2H5. He doesn't want these molecules disturbing his analysis, so he has a radical scavenger, 1,3,5 trimethylbenzene, to grab all those radicals. Also, there'll be H radicals, he'll grab them away, and then he'll make sure he's only looking at the chemistry of the parent molecule. So it's a very nice experiment, very elegantly performed. And then he has a lot of channels he has to look at. So this is for the example of this. In this case, he's doing 5-methyl hexyl iodide. So the parent molecule is 5-methylhexane, or 2-methylhexane, but we write it the other way because you number it from where the iodine is. So you start here. The first thing that happens is this molecule, 5-methylhexane, loses the iodine, so it becomes 5-methylhexyl. And now many things can happen. So he writes out all the possible reactions. You have beta scission reactions like K4. This can beta scission to form ethylene, and this alkyl radical. You could have isomerization reactions like K12. This radical can move to the opposite end. This is reversible reaction. Also, this is another isomerization. This is another isomerization. After the isomerizations, then you also have scission of those species. So he maps out all the possible isomerizations and scission reactions. And then he tries to, and then he knows eventually the final products that could be formed. So, for example, this first channel, K4, you know one of the products is ethylene. So if he can detect the concentration of ethylene, he knows ethylene has to have been made by K4. Because there's nowhere else, you look here, you find ethylene in the products. There's only one channel which makes ethylene. Similarly, he knows if you go K12, then K16, and then K9, the beta scission, you make butene. Well, there's no other pathways which are going to make 1-butene. So he knows if I detect 1-butene and the rate of change of 1-butene, I can assign it to these 3 reaction rates. And like this, he starts building, he'll start building the reaction mechanism. He'll see what products are formed. And in the experiments, they have a GC, and they have a fast sampling valve. They open the valve, they measure the products at different temperatures, and then those concentrations of those species are related then to these different pathways. And this is kind of what they will, how they'll develop. This is a log of the concentration as a function of temperature for all these different species. And then they have all the reactions, and they assign some first order rates just as a hypothesis, and then they do a sensitivity analysis, and they optimize all the rates to minimize the overall error to predict the concentrations of species. So again, it's not a direct measurement of any one rate. It's a combination of, measuring many different things, then fitting a model to minimize the rates, and then they get the final answer. So they see here for different reactions like K1, the concentrations of some species are very sensitive to K1, so they'll optimize the rate of K1 against the concentration of those species, and they'll do this to minimize the error across all the reactions and species measurements. So this is the overall scheme that you would do. You have to perform very careful and well-characterized experiments, obtain the branching ratios to all the different products. You build a first-order model with all the possible reactions. you could calculate the first set of rates from theoretical chemistry and then optimize those rates to fit your experiments. And again, these things have been done. They can probably do one experiment a year. Yeah, that's how hard they are to do. It's not a simple experiment. They got to synthesize these molecules. They got to perform the experiments. They got to build the models and then optimize or minimize the error to get all the rate constants. So, they build up over time. I think now the group is with Christine Rosada Reyes. Anybody work with the NIST? No? Nobody here does? So I don't know. I have not worked with them in the last. You did? So who's there now? Do you know? Oh, Boulder NIST. Yeah. These are okay. Boulder is a different group. They don't do the rate constant measurements. These are here in Maryland, so not far from here. Okay, so where are we now with this model? 4-methyl-heptane, it can undergo abstraction, it can undergo scission, there can be isomerizations. Now you're pretty much got rid of the fuel, but now you have all these intermediates like ethylene and propene and propyl, maybe some long chain alkenes as well. So then you got to rebuild the model. Well, or typically what we have is we have a base model with hydrogen, oxygen, carbon monoxide, methane, ethylene. We put this model on top of a base model that's well validated. But at the same time, we might still have long chain alkenes like this one here or 2-pentene. If there's a model not available for that, we have to build a model. And that's all the remaining reaction classes in the high temperature. And we won't go through them all, okay? But I go back to the slide here. So everything after reaction class 5 is just to deal now with all the different products that have been formed to make sure you're eventually coming down to small molecules which are there in your base model. And again, we won't go into all that. So maybe after the break, we will start looking at experiments. So yeah, go take a break, 15 minutes, and we'll come back.